Hello everybody, and welcome back to another installment of the Dam Control Assistant Senior Enlisted course. I'm Lieutenant Timothy Mueller, and in this lesson we're going to talk about calculating BM. Before we go into the formulas for BM, let's go back to that diagram that we saw in the last lesson and kind of build upon what we learned. So in the first lesson we talked about KB, that height of the center of buoyancy from our reference point, the keel. Now in this lesson, we're going to find BM, because like I mentioned before, we can't directly solve for KM. We have to know KB first, then we solve for BM, and then we add the two together to get our height of metacenter. So this lesson, we're just going to be talking about this right here, the metacentric radius, or the BM. Now in calculating the metacentric radius, really every single formula that does this calculation is derived from this relationship. BM, metacentric radius, equals, in some form, the moment of inertia of the water plane divided by the submerged volume. Now in order to take the moment of inertia of the water plane, we need calculus. So we're going to integrate along the longitudinal axis from all the way stern to all the way forward of each individual piece's moment of inertia, then divide it all by the submerged volume. When we're talking about ships, we can estimate this to a very, very good approximation using this formula here. But before we get into that formula, I'm going to take a look at the moment of inertia of a rectangle. So by definition, and you can look at this up in any physics video, physics textbook, whatever you might have, the definition of the moment of inertia of a rectangle that's being rotated about an axis along its longitudinal length, with this being L and this being B, is L times B cubed divided by 12. Now we had seen in chapter 0, when I talked about the water plane coefficient, this box we can bring into ship stability by taking a look, as you can see here, we can put the ship inside of a box and then estimate how much of that box is taking up, make reductions in width and length as needed, and then make a small little table here, which I found in the sources that I'll just be showing you at the end of this video. So when we take the moment of inertia here, the just basic definition of a rectangle is the moment of inertia, and then we put it into ships, we have B cubed, which you see here, times L, and then times this K being a correction factor. K takes into account this 12, and also takes into account the shape of a typical hull with these waterline coefficients. And I mentioned before in chapter 0, waterline coefficient is the amount of a rectangle that the ship's hull takes up at the waterline versus the overall rectangle itself. So here are some very common waterline coefficients for ships that are found on the open ocean. We have right around from 0.7 to 0.85. And here are the correction factors given for each individual one. So if we want to find the moment of inertia, we just take the beam of the ship, times multiply it by itself 3 times. Then we multiply it by the length of the waterline, not the length overall of the ship, but the length of the waterline, then multiply by K, K being that correction factor. All right, so now we know that the metacentric radius, this BM, is some relationship between the moment of inertia and the submerged volume, that relationship being right up here. So just looking at this, if our moment of inertia increases, then our metacentric radius increases. However, if our submerged volume increases with no increase in the moment of inertia, then our BM actually decreases. So if the numerator gets bigger, BM gets bigger. If the denominator gets bigger, then BM gets smaller. So now let's take a look at a very generic example and start seeing where these increases in I, moment of inertia, come from, as well as increases in submerged volume. So here we have a ship, and this is its condition 1, its original condition, and then all we're going to do is we're going to add weight at the longitudinal center of flotation. So we're just increasing displacement, we're not changing trim at all, and we're going to go to condition 2. So we have the ship here with a waterline here in blue, increase the displacement, and now we have the new waterline all the way up here. I've drawn out the waterline, the visual diagram of the coefficient of the waterline right here. So we have the box, and inside that box is the length of the water plane and the beam of the water plane. After we add our displacement, add that weight, now we have the ship. It was at this black, but now it's at the red. If you notice, the waterline gets a little bit longer at the stem here. So it goes from here to the tip here. And we're also adding a lot of width, but it's very close to that axis that we are rotating about. So our width that would be added up here is more consequential to increasing the moment of inertia than width added right here. If there's a lot more width added up here, then we'd increase our moment of inertia much, much quicker because that B term is cubed. So every increase is actually increased much more because of that cube term. So by adding width, but how significant? Right here, it's right near that axis of rotation, so it doesn't become much more difficult to rotate about that axis because of the additions here. The additions here, it becomes a lot more difficult, but right here, not so much. We've also added length right here. So we went from a length stopping there to a length stopping right here because the waterline went from ending here to here. That length is only multiplied by itself one time. So how significant is that? But with increasing this displacement, especially if we had large changes in the length, we increase our submerged volume greatly. Because remember, submerged volume is cubic feet. So we added breadth, we added this width, and we also added length. But we also added submerged volume. How could the ship's hull shape make this increase or decrease? And you'll see if you look at draft diagram functions of form for several different ships that you might be on serving during your time in your career, you'll see that BM has much different behaviors from one ship class to another. Now, to answer that previous question on does increases in displacement outweigh increases in added breadth and width to the waterline, we're going to take a look at our curves that we get from manufacturers of the ship and see exactly how KB and KM move. Now, these curves are ones that I got off of a merchant ship right here. However, almost every ship will have very similar behavior. KB, the transverse KB, is on this line. This is our draft going from 0 all the way to 32. So as you can see, these two are very, very extreme, with your usual drafts probably being right around the 16 to 20 area. So here's our transverse KB. Then on this side is our transverse KM. Down on the horizontal axis, this is the distance in feet. So you can basically think of this right here as our keel. Then this distance here from this line to this line is going to be our KB, and then from this line to this line is going to be our KM. Now, as you'll notice, KM, as we go from these relatively extreme drafts here, it's going to be way out here somewhere, and it dives down very, very quickly as we increase our draft. Then it starts to slow down, and it slows down very, very quickly in this kind of parabolic curve right here, eventually stopping right here, so it's going straight up and down here, and then it actually increases as we go into the more extreme drafts. So as we increase our draft, our M is going to come down to a point. Now remember when we talked about earlier with stability points, when we increase our draft, we have the waterline going up, the center of buoyancy going up, and KM coming, the metacenter coming down. That happens to a certain point. When we go outside of this point, and that metacenter actually goes up with increase in draft, that is just an extreme case where you will never be actually operating the ship during your normal mission. That will be far beyond your full load condition. So here you can see KB rises up fairly straight. It's a linear relationship between draft and KB, but it's a parabolic relationship between draft and KM, as we see right here. All right, now here in this diagram to the right, this is illustrating what happens to the ship's metacenter and overall stability when the ship is listing over to a side and we increase our displacement. Knowing what we know about BM now, BM really looks at the width of the waterplane. That's the most dominating factor in everything because it's cubed. If we list the ship over, we know that our waterplane is going to get much longer. And you can see, you originally, say for waterline 0, you originally had a waterplane like this, but then now, after you list over, the waterplane increases by that. But if we have the ship listing at a certain degree, and we increase its displacement, we maintain that inclination, but we increase its displacement. We see BM, right here, that's the original state for this waterline. But then we increase that displacement, maintain the same inclination. So our waterline really isn't going to change much in that breadth category. Maybe a little bit in the length, but not so much in the breadth. Because as we increase on one side, we're going to decrease on the other. But we are increasing that submerged volume. So as B starts to move closer and closer to the actual centroid of the entire hull, which is where the center of buoyancy would be if this was to sink completely under, B is going to move along this line. So B is going to start out here and it's going to move closer and closer and closer to the actual center of the actual centroid of the hull itself. So from B0 to B1, if we have our BM calculated, we know it's going to drop a little bit. So our metacenter along relationship to the center line is actually going to drop. So if we increase our displacement over listing, our M is going to come down lower and lower. We need to know how our G is affected. If G goes up, then this just compounds any issues that we have. But if all that weight is added down low, then G is actually going to help us by moving further and faster than M. And we can actually also see this in this curve right here, when I mentioned that G moves further and faster than M. Looking at this curve, if we typically operate, let's say right in this realm, we see that this is a typical merchant ship curves that I just found in a book. If this is your minop and this is your full load, then your KM is going from about 26 feet to about 24 feet. So you only have a range of about 2 feet, maybe 1.5 feet, where your metacenter goes from your one extreme to the other. But your center of gravity can move much faster than that. It can move on the magnitude of feet, of several feet, whereas your metacenter can only really move on the magnitude of 1 foot. All right, so that concludes this video for Chapter 3, Lesson 2 on the actual metacentric radius of a ship. We had talked about KB, the height of the center of buoyancy, in the first lesson. Second lesson, we're stacking on top of that the metacentric radius. So we add the two together and we're getting that KM. And this is where we derive this curve right here. That does it for all the lessons that I have for Chapter 3. In the next video, we're going to go through an example problem in an Excel spreadsheet that I made with just a box, a rectangular barge, and we're going to actually derive KM, KG, KB, KM, and we're going to see all these curves in action. We're actually going to draw this curve here, we're going to draw this curve here, and we're going to see how a very generic hull shape, when we start doing the math to it and start integrating, we'll develop these relationships here. But that's for the next video. Until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.